Welcome for this webinar, where I'm very glad to be with so many of you, and I'm very glad to be hosting Ramon Calvo from the DLR. And we will start this webinar with a short poll, just to know very briefly how much you know about laser communication, adaptive optics, and MPLC. And then we will switch the presentation in itself, and I will let Ramon have a few words. So I guess you should see the poll right now, and you should be able to answer it. We will let it probably 1 or 2 minutes. There are only a few questions. Or not. I'm not sure. I'm not sure the poll is working. If you don't see it. Okay. Okay, I'm not sure. Maybe I did something wrong, but I don't see the results here. All right. Okay, then I guess I'm not sure. So in any case, I guess we can switch to the presentation. So I will let Ramon introduce himself and introduce you laser communication and what about it. And so Ramon, I'll let you.
So good afternoon. So I'm engineer at the German Aerospace Center. So I'm leading a group on optical communications for satellites. And today we'll present the joint measurement campaign we had last year with Cailabs for comparing adaptive optics systems with the multiplane light conversion. The goal here is coupling light to the fiber. And that is mainly done. This task is done with adaptive optics usually. So as we knew the technology from Cailabs, we decided to join efforts and to make this comparison in order to investigate possible alternative solutions that work under strong turbulence conditions. So I will start with the presentation. So I will have some words about the motivation and then on adaptive optics. Then I will hand over to David for the multiplane light conversion. And then the last part will be about the measurement campaign we had and then the results, further steps. So the motivation for satellite communication. So usually with few satellites, one can reach worldwide coverage. So the goals of the Institute DLR is to provide global connectivity, so internet access everywhere. So usually currently, the current technology is based on K-band and radio frequency, where both the user link and the feeder link are both implemented radio frequency. Some of the examples are KSAT or PSAT, the different versions. And all this technology is based off multiple gateways, radio frequency, which fits this satellite. So the number of gateways that you need to reach certain capacity on the system increases linearly with the capacity. So you see here the graph on the right part. So they are the comparison between different bandwidth. So if you consider only K band, if you consider Q and V band, and if you consider adding also, for example, the so the bandwidth which is available in all these cases is limited to few gigahertz. When optical horizontal line, this purple line, which is set to 11, which is a rough estimation of the number of ground stations that you require to have clear sky conditions. So one single ground station can provide the capacity that you require, because the bandwidth available for free space communications is about 10 terahertz, and it's bandwidth which is not regulated. So it's available, and the optical communications is very directive. One can avoid any interference. For that, we have topics like onboard processing. We need switching, and atmospheric turbulence is one of the challenges. That is for geosatellites, but for satellite communication, as in the last year, there was a lot of different proposals based on constellations of satellites, even in MEO or in LEO. And some of the examples like Laserlight or Starlink space, then it's based on multiple satellites from tens of them until thousands of them. In that case, all these constellations are based in optical intersatellite links. The MEO constellation is also based on feeder links, based on optical technologies, where the Starlight is relying on the radio frequency technology. Also, some developments in that direction goes also from the ESA with the concept of iron, which is a concept of creating a network of satellites on the sky, which practically extends the terrestrial fiber network towards the space. So I go towards the next slide. So, as I mentioned here, we would like to extend this ground network to the space with different satellites, including LEO, including GEO. But for that, we need fiber coupling. So we are relying on the optical technologies developed for fiber communications. And that means we come out from a fiber after modulating the amplification, and we need to come back to a fiber to use, for example, DVDM, so multiple optical channels together in order to reach these data rates. So availability is a key. And as I mentioned before, in optical, one ground station can provide the capacity because the bandwidth is there, is available. The main drawback there are the clouds, are the clear sky conditions. So you see here on the upper part, a map of Europe with the cloud availability. This is a mean cloud. So the red parts are where more clouds are there, and the blue part, the more cold parts, are where clear conditions are more. So you see around Mediterranean Sea, there are less clouds. If you go to the north of Europe, there are more clouds. At the end, the concept is based on a network of ground stations. So the graph before, you saw this line at 11, so 11 ground stations. So you need 11 of them because you distribute them around the whole geography where you have the coverage of the satellite in order to achieve a decorrelation between ground satellites. In between ground stations. So it means at least one of the network will be available, will be cloud-free. The other point here to consider with optical, the optical channel is the turbulence. So the turbulence means the atmospheric distortions needs to be compensated, needs to be taken into that. We go with adaptive optics as a standard approach, and we also research on alternative approaches. And that is more or less our way of working in DLR. So we test our technologies there, we make experimentation, and we have collaboration within with the industry. And that allows us to further investigate different options and different technologies. About turbulence, just some words. So if you see here in the left part of the slide, you see the transmitted beam. So it's usually it's assumed a Gaussian beam, which is symmetric. We transmit it through the atmosphere, and the atmosphere has different cells where different index of refraction due to temperature variations, also on a small scale, produce these phase distortions, these phase deviations along the profile of the beam. So it means when it transmits, this different phase self-interference that sometimes can be constructive, sometimes can be destructive, producing this pattern that you see in the right part with multiple speckles, with more light or with less light. That means that when we transmit path at the receiver, so depending on the receiver how it looks like, so we'll receive more or less light depending on the turbulence and these turbulent changes. And the dynamics of that, it's on the millisecond. So the atmospheric evolves with a kilohertz bandwidth. So it means every millisecond we can expect another kind of distribution and intensity and the phase distribution. So if we look more towards the satellite configuration, so the satellite has divided, and we can divide in two links, so the downlink and the uplink, which does not travel through the same path. And that is due to the point height angle. So the satellite is moving, so if over the same direction where the downlink is received, we will not find the satellite. So what usually it's done is one receives the downlink, one tracks the downlink in order to stabilize the received signal and use this information to pre-correct the uplink and send the point ahead the beam toward the satellite. So that means the distortions that we are measuring on the tilt for the downlink are not the same ones that for the uplink because of the point ahead angle. So it means the distortions can be correlated, but are not exactly the same. So it means the uplink will depend on a residual beam wonder, residual tilt, which will produce fluctuations on the signal. So you can see here, two examples for the uplink and the downlink. In the upper part, you see the blue signal is the received signal of the satellite. The satellite acts like a point receiver. So the beam after the propagation is huge, and the telescope of the optical terminal on the satellite is like a point. So you received a signal which will be not, so it will be just a point on the whole field, and so it means you will have a strong fluctuations there. That's on top of that, you will have also beam wonder. So it means the uplink tilt will also move your beam right and left, up and down. So it means it will produce extra fluctuations. For the downlink that you see in the graph below, usually telescope diameter is bigger than the speckles, that the size of this distortion. So it means the telescope is averaging the effects, so you will receive some light. And if you see here the blue signal, you see there is a signal which is changing with you see the variations, but which are much more smaller. That is the effect of the aperture. But on top of that, in downlink, you need to couple the light into the fiber. So if you try to focus this 1 meter collecting light into one point, you will not receive a nice and symmetric point, but you will receive speckles, which depend on the phase distortions on your aperture. So the approach is to correct these phase distortions in a way that we are able to couple it to a single mode fiber. And this problem is similar in some sense what you see also in astronomy. The astronomy, it's similar in the sense that you, with satellite communications, you want to observe one direction where you have a planet, for example, and you have a lot of light, and you have to integrate a lot of time, and you take as a reference a star, which serves as your downlink, and you try to compensate, for example, the tilt using a nearby star. So here is similar. In that case, the star, it's the same size moving and the planet, just to make a comparison with astronomy. So talking to adaptive optics, so if we look to the requirements, so we have requirements than in astronomy. in that sense, because we are targeting also lower elevation angles. For geostationary satellites, we are targeting 30 degrees, maybe 20 degrees. For LEO satellites, even lower, because we have to maximize, first of all, the coverage, also for the geostationary. So if we go to higher latitudes, then we will not have a coverage of the geo if we limit too much the elevation angle. And then for the LEO satellites, we have also to maximize the time of the contact. So the LEO satellite is crossing the whole hemisphere, so we have to be in contact with the satellite as much time as possible. On top of that, there is also the slew rate, for example, in case of the LEO satellites, which makes the turbulence changes faster, because it's like a virtual wind that you create by crossing the atmosphere. On top of that, the satellite communications needs a 24 hours of operations. It means we have to work also in daytime, where in astronomy, usually the observations are done only during the night. We need also ground stations which are more compact and more relative less costly, I would say, than in astronomy. And but we can also rely on some adaptive optics technology which they were developed also from astronomy, which is where it is a mature technology, has to be further developed for communications. So the second technology is the multiply line conversion. So in that case, we have the light coupled into a multi-mode fiber, and this light is split in different single mode fibers. There's an optical coherent combination of the different fibers, but it's a passive and compact system. And this multi-mode interface makes the system quite simple. So the idea in the background is then to get a compact solution for fiber coupling downlink, for transportable stations, and eventually also combine both systems, combining active optics and multiply line conversion to achieve as much reliable fiber coupling as possible. So our goal here in this measurement campaign was to compare both systems and see how the performance look like. So for the adaptive optic systems, we had a wavefront sensor with an 8x8 sub-aperture, a Shakarman-based wavefront sensor. And we used the Xenix Cheetah camera, which was running at 2 to 3 kilohertz. So for the ephemeral mirror, 97 actuator mirror from Allioux. And the control system was built on C++ and Python, running a real time computer, where they had a latency below 50 microseconds, so which allowed quite fast frame rates. And the control system here was based on an integrator. So here you see the scheme on the right part of the adaptive optics system. So where the aberrated wavefront is a received wavefront that goes towards the ephemeral mirror. And then it's splitted with a beam splitter and goes to wavefront sensor, and the wavefront sensor drives the ephemeral mirror through the control system. And then you have the high resolution image, or you have your fiber coupling at that part after the correction of the ephemeral mirror.
Okay. Okay, so I will say, before I present the MPLC very precisely, just a few words about Cailabs, because we are not very, we are a pretty young company, so we might be known, we might not be known by everyone. We were founded in 2013 with a unique technology called MPLC that I will present. And our expertise is really in optical beam shaping. So we developed several products around that, from laser processing with a product line named Canunda to local area network to improve the capacity of old fiber, multimode fiber in local area network. Also some research and development in optical fibers, but for the, let's say, future of optical fibers, and custom development, for example, for LIDARs, for defense, for future of optical network inside plane. And the product that we are talking today is named TILBA. Why we present always that is because there are some, the technology, the core technology inside all of these products, same, are synergies between the products. For example, we handle hyper laser for feeder links, which is the same technologies, and for laser processing, or at least similar than for laser processing. This is one of the examples of the synergies between the products. This is really the core technology that we develop at Cailabs and that we work with. It's a technology that is derived from quantum. The idea at the origin was to manipulate the quantum state of light, a spatial state of light, and it's a technology that is fully passive and based on a succession of faceplate and free space propagation. The idea is really to, so I just take this, yeah, so you should see my mouse, I hope. So thanks to a succession of faceplate and free space propagation, we're able to perform any what we call unitary transform. So performing any transformation, the shape of the light. So for example, on the image of the left, you can see at the input a Gaussian beam that is transformed into a donut shape or a Gaussian beam thanks to a succession of faceplates. And what is interesting with the MPLC is the fact that you can manipulate several modes at the same time. So perform a transform from a unitary basis to another unitary basis. And for example, in the image in the middle, we manipulate 7 shapes at the same time. So it's not very clear, but there are several Gaussian modes at the input here on the image of the middle that we transform simultaneously. So we do spatial mode multiplexing. We transform them all simultaneously into modes, another basis at the output. Here it's a linear polarized basis, but we can use also several other bases like Gaussian modes or Hermite Gaussian modes, and or any type more or less of basis that would be interested. In terms of implementation, it would be too complex and too bulky, and also you would have too much losses if you implement it in transmission. This is why we implement it in reflection. So on the image on the right, you see that there is a fiber array with its 7 Gaussian beam at the input that we manipulate thanks to a succession of reflection here on the faceplate. So it's still faceplate and free space propagation. And thanks to this reflection, we now manipulate the shape of the light to the output that is a multimode fiber here, and we couple 7 different modes inside the multimode fiber. What is also interesting with this technology that here it's a telecom design. So we have a fiber array at the input and a multimode fiber at the output, but in principle, it can be exactly the same if we remove the multimode fiber or the fiber array at the input, and we can have like this free-form transform from an input basis toward an output basis. It's convenient, for example, if you want to play with modes that are different than fiber modes. For example, you can do, I don't know, square. If you generate a square flat top, it doesn't fit inside a multimode fiber. And also, of course, it's completely reversible, so you can use the multimode side as the input and the monomode side as the output, which is what we do in practical when we use the MPLC for laser communication. This is a picture of an MPLC, so it's exactly what it looks like in the reality. It's approximately the size of half a smartphone, so it's this size, I would say. And what is also interesting is that this technology is passive, it's bulky, it's very, and it can be done it can be designed very compact, with very compact component. And for example, we have a project with Safran Electrical and Power, when the goal is to put MPLC inside airplanes. And for this project, we developed MPLC that are very small, that are the size of a 2-euro coin, massive, that are compatible with temperature, pressure, vibration, and shocks inside an airplane. So it means that it's a component that is relatively robust. And when we speak about laser communication that could be transportable, for example, I don't know, maybe inside an airplane or inside a drone or in a vehicle, it's very convenient to have something passive, robust, and that is compatible with I would say extreme conditions. Very, very. Here are some examples of what we can do. It's just to show that it's relatively versatile and that there are different applications that are interesting with the MPLC. For example, here on the top left, we have a square, a flat top square that is interesting for LiDAR imaging, for example, for active imaging. On the bottom left, we have a Hermite-Gaussian mode. It's one of the modes that you have in the multimode fiber. In the middle on the right, we have orbital angular momentum that are interesting, for example, for quantum distribution. That is also a topic of interest at the moment in laser communication. And the other shapes just show that it's relatively versatile. Why is it interesting? It's interesting because in theory, there could be some modes that are more interesting for laser communication than others. For example, if you have a circular profile, using Allioux mode might be more interesting. And so it's good to know that we can do several different. And now, more practically, what do we want to do? Mitigate atmospheric. This is, to me, one of the most important slides, because if you understand this really well, you understand what we can do and what we want to do with the MPLC. If you have one of the techniques to compensate for atmospheric turbulence is to use, for example, adaptive optics. And even if it's not really a Cartesian basis, because you will use the Zernike polynomials and you will modify the deformable mirror and also with modes, what you do basically is manipulate a mirror to be able to reproduce the shape of the light that you would have. So you have a deformable beam that you modify thanks to a deformable mirror to reproduce a Gaussian material. What we do is not modifying the shape of the light like this, but decomposing the light in different modes. And it's because we use, we are very familiar, we are very good at manipulating the shape of the light and very good at doing spatial multiplication. So what we do is that we decompose the perturbated beam that we have here into a limited number of modes. Here it's Hermite-Gaussian mode, as I said previously. It can be also on other basis. And we then transform each mode individually into a Gaussian beam that we send to a single mode fiber. So like this, we do really special demultiplexing, and we can send a perturbated beam to several single mode fibers. In practical, we implement it like this. So it's really what we want to do and what we are developing. It's having a single mode. We have a nice Gaussian beam at the input. It's perturbated by the atmosphere. You have pointing mirror. Then you have a perturbated beam that will receive at the multimode fiber side, at the input of the multimode fiber. You decompose it into a limited number of modes, Hermite-Gaussian modes, for example. And then we decompose it thanks to the MPLC. We do special demultiplexing, send each mode to a single mode fiber. So why is it interesting? It's really because you will still have fluctuation of the phase and amplitude of your mode, but this fluctuation will be sent, will be transferred. This complexity will be transferred inside the single mode fiber. So you will have fluctuation of phase and amplitude inside the single mode fiber, and this is much easier to process than having fluctuation of phase and amplitude in free space of several modes that you don't know how they behave. And the idea really is to have a passive component that is relatively standard and plug and play, and that is easy to integrate. And I will come to that after. Probably the last thing is here we developed a component, we use the component with several single mode fibers at the output. This is the component we use here. But we are also developing a box to be able to recombine several single mode fibers, to be able to have something even more easy to integrate, I would say, and easy to use. So more concretely, what did we use? What is the component with together? it's a 10-mode demultiplier. It was designed around 1550 nanometer. And when I say it's relatively standard and easy to integrate, it's because we have here a multimode fiber that you can, it's a precision graded flexible fiber. So it's something that you can buy that is off the shelf. It's relatively standard. We use FCPC connector at the input of the multimode fiber. And we use 10 single mode fibers at the output. So when you look at the 10 and want to do the component, you have FCPC connector, multimode fiber, the multiplexer, and then FCPC connectors after your single mode fiber. So it's relatively easy to install. You just screw it in there, and that's all. And in terms of performances, it's also important to say that the installation losses were around approximately minus 2 dB, and something that you need to integrate in terms of your overall optical performances. Finally, the last thing that I wish to say is that if you look at the performance of the content at other wavelengths, we tested the content on the whole C-band. It's relatively stable. So here you have on the top you have the insertion losses, and on the bottom of the graph you have crosstalk. And what you can see is that overall the whole C-band, the performances are relatively stable. And even if you go to the L-band, you will still have some approximately the same curve, something that is approximately stable. So it means that you can use this type of content with a WDM signal in theory. I guess that's all I wanted to say on the MPLC. And so I give the lead to you, Ramon.
So this is the block diagram of the experiment. So we had here the telescope coming from the satellite with the emulated terminal satellite. Then we have fine steering mirror. And then we have, from one side, we have the multi-fiber coupling for the MPLC. And from the other side, we have the adaptive optics system with the deformer mirror, the Shakarman wavefront sensor. And then we had also free space photodiode, for example, for measuring the power. We have the single mode fiber coupling, also with the photodiode after the coupling. And we had the focus camera. So the test was done in a 10.5 kilometers link between Weilheim, that is 80 kilometers from DLR, and there is also a DLR infrastructure there, and the weather forecast station in Hohenpeisenberg, which is on top of a mountain. So we had a profile which is from the valley to the top of the mountain, but as you see, there's also some small bumps in between. So it's quite close for a low elevation angle link, so quite horizontal link. But we try to emulate this gradient on the profile of the turbulence in such a scenario for satellite communication. So what we use it here is to compare it with the theory and try to estimate the CN square profile based on the altitude over or the height of the line of the sight from the ground. And that led us to conclude that this is similar to satellite link under worst case conditions in terms of the turbulence. So on top of the terminal that looks like that. So we have here, as you see here, the white box is containing the whole optics and electronics. This black round tape with the logo, that is the entrance of the receiver part, which also can be directional and be transmitter part. And then you see here this linear stage with a collimator also on top of that, which we can adjust. For that, we can emulate also the point head angle when we do also experiments. So we separate the transmitter and the receiver part by separating them physically, since the terminals cannot move, of course. In that case, we don't have adaptive optics because simulating a satellite, and the aperture of this terminal is set it up in a way that emulates what as a point receiver for the reception part as it would be in a satellite. In that case, for this experiment, we use the transmitter since we were analyzing the fiber coupling, and on the other side we had the terminal emulating the ground station that was at the Weilheim location. And in that case, we had adaptive optics. And we have also the turbulence monitoring allowing also, we had also a bidirectional link. So we had uplink and downlink active. So we use the downlink to track and to point towards the uplink. So in that case, if we look a little more on the terminal, we can see here the primary telescope. The orange line is the receiver, the downlink. So it goes towards the tip tilt mirror, which compensates for the tip tilt. And then part of the light is split and goes to the MPLC from Cailabs, which is fiber coupled, a multi-mode fiber. And then part of the light goes forward to the deformer mirror, and then toward the system with the 4-quadrant detector, also with the focus camera, wavefront sensor, and so on. And the green line, as you see here, is used for the uplink, so for transmitting up. And to keep both, to keep the system, so the link aligned. Here you see the integration of the MPLC on the test. So it's this black box here. Here contains the MPLC, and the yellow fibers are the single mode fibers, which goes to different receivers, different detectors. So we had 10 photodiodes, one per single mode fiber. And then the photodiodes were digital converted with Pico lock. So where we have 10 input channels with 10 kilohertz per channel. And it was a sequential sampling. So it means we had the first channel is sampled, and the second, the third, the fourth, the 10, until the 10th, and then again. But that's with 100 kilohertz data stream. So at 10 kilohertz. So what we did is to quantify the performance of the MPLC. We digitally combine all these 10 inputs. So what we did is we oversampled the signals, and we align it, knowing the separation, the time separation between channels, and then we add it together in a way to get the combined signal. So everything together, also with the measurement system, so the turbulence and the wavefront sensor and everything was saved on binary files, and we use it then afterward for analyzing the data. Here you see a small image on the adaptive optics system running. So here you see Shakarman sensor and also the DM actuators commands on the top figures. And then down you see here the actuator commands, let's say on a XY scale. And you see from the left part, there's a weak, and then from regime, you see down the right part. So you see here the difference on the actuator hop stroke, where it was applied towards the formal mirror. You see also here in the image of the Shakarman, which is on the left part and the upper part, so the both left images with the grid. You see here the influence on of the strong regime. In that case, we have a strong turbulence. We have also scintillation. So most or some of the lenslets were not illuminated due to the scintillation. So it means in that lenslet we cannot estimate correctly the phase. So this is one of the challenges on the strong turbulence with the standard Shakarman sensor, which some of the lenslets cannot or are not illuminated. And you see it from the weak regime. So most of the subapertures are well illuminated. So you see here really a difference. Because this difference here between the weak and strong regime, we will see also on the performance of the adaptive optics. You see the residual root mean square wavefront error. You see it here, the blue crosses are when we only make tip tilt correction. So it means there is no adaptive optics in the sense that we are not correcting any aberration. We are only correcting the tip and the tilt. And then the red circles are when the adaptive optics correction was applied. So you see here the adaptive optics corrects for the phase distortions, but you see also that this correction it's becoming worse also with the scintillation, with increasing the scintillation. Of course, the wavefront error also increases with the scintillation, with the strong turbulence, I would say. And you see it with the blue crosses. but also the residual one is increasing. So we had here the scintillation, so we had drops of more than 20 dBs. We had a subaperture diameter, which was around 1 centimeter, 1.25 centimeters. So it means that during this strong scintillation, some of the subapertures, as was shown before, were not illuminated. So we had a really high dynamic so for the waveform sensor. So if we compare, we can classify the measurements. We took the scintillation as a parameter. So we said, okay, everything from the scintillation below 0.1, we can define it as weak. And then as a medium between 0.1 and 0.3, and then all 0.3 is really strong effects of the turbulence. And then if we plot with the free parameter, we see also how the free parameter decreases towards, let's say, scintillation. We classified in that way in order to quantify also the performance of the adaptive optic system in these three regimes, so where the scintillation was more active, where we saw that is the most limiting factor of the adaptive optic system. We also measured some parameters like the aperture averaging compared with the free parameter. So the free parameter was estimated from the Shakaman sensor. And then with the aperture averaging, we measured like how the scintillation also was changing with the free parameter in these three regimes. And you can see quite well with these three regimes that we defined before for the scintillation, that the aperture averaging was higher for higher, let's say, weaker turbulence, and then decreasing by a stronger turbulence. So you can see quite well these three regions of the three colors in this graph here. So we had an estimation that this under weak turbulence, the correlation width for the speckles is around 5 centimeters. So it matched quite well with the aperture averaging factor measured. We had an aperture of 10 centimeters for the receiver. So here we can see then the results. So we had here double epsilon axis. So we have on the left part the scintillation, so the fluctuations of the received signal. And in the right axis, we had the free parameter as a reference value, calculated, as I said. Then we have the blue circles, which is the Cailabs MPLC performance, so the fluctuations of the digitally combined signal after the Cailabs MPLC. So combining all these 10 inputs of the single mode fibers digitally. So we had this measurement of the scintillation of these normalized variants of the signal. This is the blue circles and the blue crosses. Then we had a photodiode before coupling and after the adaptive optic system, but before coupling. So that's the red circles. And that is a photodiode which is large enough to catch all the focal image. So it means the red circle represents the best we can get. So it's our goal. It's focusing the 10 centimeters aperture of the telescope towards the photodiode. And that is our reference. So better than that, we cannot do it. And then the part is after the single mode fiber coupling, after the adaptive optics system. So it means we had the adaptive optics correction, and then we focus the light into a single mode fiber, and then we measure in the fiber what is the signal fluctuations. So at the end, what we are comparing is the blue circle or the blue symbols with the yellow ones, putting as a reference the best we can get, that is the red ones. So here we separated the results in these three regimes that we defined before with the scintillation. So the weak and the middle, and then the strong, the medium and the strong. So in the weak, here you can see The red ones, as expected, are the lower, so it's the best we can get, so it's the less fluctuation that we can get. So on the right picture, you see only tip tilt correction. So in that case, only the tip tilt was active, and the tip tilt was active for both paths, for the Cailabs MPLC and for the single mode fiber coupling, so for both paths. And on the left part, you have the Allioux correction. So it means the deformer were also active, and it was correcting aberrations for the yellow markers, so for the single mode fiber. So you see here that with only tip tilt correction, so you get after coupling less performance than expected for the MPLC. And when activating the adaptive optics system, that you see that sometimes the performance is a little better, sometimes it's a little worse, but it's really similar. So we are quite on the same way. So I mean, the adaptive optics system is correcting the phase distortion, and we are getting similar results with both systems. So if we increase the turbulence and go to the medium, you see it here. So you see the parameter that is this black stars, it decreases. Then you see here that the separation between the blue and the yellow on the only tip tilt correction, so on the right part, increased. So it means we have more turbulence effects, we have more phase distortions, and that means the single mode fiber coupling it's less performant. So here we have a more distance because we are only correcting the tip tilt. So when we activate the adaptive optics system, we see that the yellow and the blue markers comes closer. So we see here that the performance is also really similar. Sometimes a little better one, sometimes it's better the other one, but they are really similar, and we are quite close to the red circles. So in that case, also both technologies are correcting pretty well and the turbulence, the effect of the turbulence. And finally, on the strong one, we see it here. The free parameter decreases a little, and then we see here much higher distances between the red and the yellow markers. And you see here on the left part, then the MPLC, it's performing a little better in most of the cases, also for a strong turbulence, but the performance is quite similar. So as a conclusion, so we had this empirical comparison. So we just decided, let's try what happens. Let's plug the system together and measure them together and synchronize the measurements in a way that we see at the same time what's happening in both systems. So we compared the system from Cailabs, and we compared our adaptive optics systems for single mode fiber coupling. And we see it as an interesting technology because it provides, the MPLC provides a quite compact solution for free space optical communications. And we found that the performance is in both systems, and it seems that the MPLC is a little more robust for strong scintillation than the Allioux implementation that we have. So the next steps, we would like to continue investigating this technology. We would like to test the equivalent combination of the output of the single mode fiber. So until now, we digitally combine all the outputs, but the idea is then we don't have 10 outputs. We have only one single output. So the idea is to further test together with Cailabs and do more measurement campaigns to characterize better also the performance of the system, and also to try this equivalent combination. And we are planning also a joint measure here if the pandemic situation allows us to proceed like that. So that's all from my side. David, I'll give you the word back to you. I think you are muted, could be.
David, I think you are muted.
So the ground station, we limited the aperture of 10 centimeters, also for practical reasons. So we are transporting these terminals quite often. So it's not a big telescope, so it makes simple to just install that. It's mainly the reason of the 10 centimeters. Maybe we would have a little bigger one. But this everything is scaled down, also the adaptive optic systems and everything. So usually the satellites, if you have a satellite link, combination between a link between a satellite and the ground station. The ground stations depends where is the orbit of the satellite, but it could range between 40 centimeters and 1 meter. I would say that these are quite a range of possible sizes of the telescope diameter. In that case, the limitation, I would say, is not on the size on the ground, but more on the satellite. So we're limited on the weight, and you need something that is compact and quite robust. So on the satellite, you would place smaller apertures. In our demonstrator, so we put an aperture, which is, so we can set the divergence of our beam. So we have more than 1 collimator. We don't have only one centimeter. So we choose it in a way that we can well illuminate the receiver part in a way that the beam is not too Gaussian, but we have enough power for experiments. So the idea was to emulate the downlink as good as possible. So that is why it's also the asymmetry on our testbed. It's also there because we try to emulate also the asymmetry that we have on the satellite. In that case, the 1 centimeter, it's more towards the 8 meter. So for the receiver part, we have a 5 centimeter, so it's a 2 inches lens. We have also an iris, so we can also regulate that in a way that the receiver part, it's not seeing multiple speckles, so that acts as a point receiver. So I hope that answers the question.
Okay, so sorry, apparently I was mute. I guess you should hear me now. So concerning the different strategy, there are different strategies to combine the several single mode fibers towards one single mode fiber. The one that would be probably the more interesting, at least in terms of performances and commercialization, is to use integrated photonic chip. You have several single mode fiber input. You manipulate the phase and intensity thanks to, for example, Mach Zehnder. And like this, you can recombine coherently the channels, for example, 2x2, but there are several strategies that you can think of, to have a coherent interference between the several channels to have in the end all the signal in one single mode fiber. It's one of the strategies. There are also others, for example, in free space or using fibers. And if you are interested, there is some literature that I can send you on the subject. The main limitations will probably be in terms of throughput. You need to make sure that you design very well the circuits and also interface to have a very high typically the difference between the size of the channels. And in terms of performances, if you design well the system, you can have a chip that is compatible with the system that is compatible with very high throughput, for example, up to 40 gigabits per second. But in any case, you will increase the radiation losses. And this is one of the main challenges that we are working on at the moment, decreasing the insertion channels to have the best optical band. So I guess this is for Ramon.
So the deformable mirror had 97 actuators, and we had an 8x8 lens-led array for the waveform sensor. So the mirror, just for information, we use the Allioux mirror with 97 actuators. The waveform sensor, we did it ourselves. So we design it, and then we bought the lens-led array. We integrated with the camera, and the camera was a Xenix Cheetah.
Okay, the next question is also for you, I guess, Ramon. In terms of insertion loss penalty in the Allioux and the MPLC, it's 2 dB of insertion loss. What about the adaptive optic setup?
In that case, I don't have the number in mind for the insertion loss. So usually in the lab we get like 60-70%. So if there is no distortion, so we go closer to 70%, and I assume it's about 3 dBs for operation, 3-4 dBs loss for during the operation.
Okay. Could you use the MPLC for turbulence precompensation? That's a very good question, and it's really something that we would like to try. In theory, it's doable. You just need to manipulate the phase at the input of the MPLC to choose the mode that you want to excite with the phase that you like to shape the beam at the output. So it's something that is doable. It's very similar to experiments we did for coherent combining. The only thing is that for coherent combining at the output, you want a Gaussian beam. And if you want to do precompensation, you don't want a Gaussian beam, but you want a shape that precompensate the turbulence. So it's something that is doable in theory. Of course, there would be some limitations, probably in terms of the main thing is that we fabricate for the moment the MPLC block, and if we want to do some turbulence precompensation, we would need to partner with some probably some academics, some laboratories or industrials to have feedback on the turbulence and know how to analyze it to excite well the MPLC. So it would be we would need to think about the system together with someone else. But in theory, yes.
Maybe just a comment on the last question about insertion loss. So one of the things that we focus is on the variation because at least if we compare with astronomy applications in satellite, we have quite amount of light. So what for us is really important is the stability of the signal. So if we have 3 dBs more, of course, the more dBs, it's the more power you need to send also from the satellite. But I think the key part here is the stable of the signal. So if I can take into account my link budget, 1 or 2 dBs of extra insertion loss due to one system, adaptive optics based, MPLC based, whatever based, but I get a signal which is really, I would prefer than having less insertion loss, but really huge strong fluctuations, because the strong fluctuations requires, when we are transmitting data, requires coding, and that has a really strong impact on the power you require also for processing, and also complexity of the system. So you need to code the data before sending from the satellite, and you need to pre-process it afterwards. So that's why for us was more the focus, more than analyzing the insertion loss or comparing insertion loss between systems, was the signal stability. I think for us this is more the key parameter. Sorry, I interrupt you for the next question.
No, it's perfect. Thanks. Okay, so I guess we'll stop with the question now because it's already 4 p.m. and we were supposed to stop a little bit before that. So thank you very much, everyone, for attending this webinar. Thank you very much also for thank you very much, Ramon, for being here today and presenting to us. And I don't know if you want to say a last word, but that's it for us.
Thank you for attention. If there is any question, also for the experience we did, for the measurements, for whatever, so I'm also available also to answer further questions per email. I think you will provide contacts, and there is a possibility to get more information.
Of course. Thank you. Bye.